Okay, so we now have points. We have scanned them on the surface, and now we're going to create some products. And the products you're looking for, basically two. One of which can be a digital surface model. So that's the topographic data, but it's of the first surface that's intersected by the laser. So it might be vegetation, it might be a ground surface, it might be trees near a house, it could be the house, or a large building. And we refer to this as the digital surface model, because it's an elevation model and it's on the surface. We use digital elevation model only to refer to the elevation of the ground surfaces. And so the next part that's going to be necessary is to do some kind of filtering on your original data set and turn your digital surface model into a digital elevation model. Now, some people use the term digital terrain model to mean digital elevation model, and it probably makes sense to use digital terrain model because then that tells you exactly what you're looking at. So what we need to do in order to get at the DTM is to do point classification or filtering. DTM is digital terrain model. So we need to remove all the points above the bare earth surface. And the process of doing that is can be called point classification or filtering. And it's the necessary prerequisite to analyze topography or surface conditions, as the bare earth elevation is almost always needed. Now, this wouldn't be true in a perfectly bare surface, so like an ice sheet or the Bonneville Flats, but generally, if you've got any kind of vegetation or similar, you're going to have to do the point classification. So what's the error budget for a surface model? Well, your Z error is going to be a function of measurement error, classification error, and interpolation error. So the measurement error is, the sort of fundamental, how well can we measure the surface location, not thinking about what kind of surface it is or where it is in the canopy, and that's about 15 centimeters vertical and 50 centimeters horizontal. Now you might wonder why those two things are different. 15 centimeter vertical is basically the accuracy of the GPS. That's the error that is on that particular measurement, the elevation of the plane. The 50 centimeter horizontal is due to the IMU or the INS, the inertial measurement unit or the inertial navigation system, because it's harder to measure the roll and pitch of the plane than it is to measure its location. So that's why you have two separate components of measurement. It's actually due to the errors in two different parts of the sensing system. Interpolation error, we'll see as you take away points that are not on the surface, you're going to have to fill them in somehow. We're going to use some kind of interpolation. That's a function of how many points there are on the ground surface and to some extent the canopy cover. And the classification error is a function of vegetation height. That's because if you make a misclassification and call a canopy return a ground return, then the higher the vegetation, the more of a difference you're going to get, all other things being equal. So misidentifying canopying as ground is much worse than misidentifying ground as canopy. Again, if you misidentify canopy and think it's ground, you're going to have your ground suddenly come up from the rest of the surface around it. Whereas if you misidentify the ground as canopy, it's just going to be that you have another point lying down near the ground surface. That is canopy. That doesn't really affect your processing. However, if you're talking about point classification, if your algorithm tries to make as many of the points as possible canopy, then you're going to wind up with too few points on the ground surface, and therefore you get a larger interpolation error. So the errors are not independent. Issues for doing point filtering. The first one is just the volume of data. For a county level project, you could have 3 billion points for about 2,600 kilometers squared. That's a lot of points, not only to store, but to process. There are a number of classification or filtering algorithms that have been developed. Many are proprietary, so you don't know what's going on inside the algorithm. The filters have not been tested for different data sets with various types of landscape features. So there's not a good way of knowing what parameters you'll need to supply to the algorithm in order to get good results. They just kind of play with the various parameters that can affect the filtering or classification algorithms, and until they have something they think is right. And they do have GPS GPS observations they do in the field in order to figure out, have some way to independently verify the DTM that they're creating. Some of the errors are not going to be documented very well unless you really insist on it. And the sensitivity of these filters to the parameters that go into them and the sensitivity to data resolution generally has not been analyzed because you have proprietary systems. There are a couple of different approaches to point classification. There's a slope base system, and what that system says essentially is any point that is more than any point which, relative to the point around it, implies a slope of greater than some threshold, that's going to be canopy, right? Because slopes only go up to a certain amount. There's the block minimum approach, and that's an approach where you say any pixel that's not within a few meters of the ground surface is going to be a canopy system point. There's a surface-based system where you're fitting equations to the data you have, and if a point has a large residual from that surface, then that's a canopy point. And then there's clustering and segmentation approaches that I won't get into. But basically, it's finding objects that are higher than the rest of the surrounding points and classifying the ones that are higher as canopy. So block minimum algorithms are very popular. They're commonly used. Basically, it's just saying that the ground return should be the lowest elevations in a local neighborhood. But of course, you're going to have some neighborhoods where you don't have any ground, or where you certainly might not have any ground surfaces. So that's a problem that you get. So it has the potential to be biased low in high slope areas because the minimum elevation of a certain footprint is always going to be the lowest point in an area. So that's going to bias you low. And you can use multiple or overlapping spatial filters, just showing that a little bit on the right. There's an approach called the elevation threshold with expanding window, which kind of looks at the the minimum elevation as you look over larger and larger blocks or larger and larger areas on the ground, from say 1 meter to 2 meters to 4 to 8 to 16. And at some point, you're not going to see any change in the elevation of the DTM because you have found the ground surface. If you have small blocks, right, the minimum may be at the top of the canopy. The larger the block, the more likely it is that the minimum elevation is going to be on the ground surface. And so, yeah, when the block size has increased to the point at which the minimum elevations converge, the points that make up those minimum elevations are mapped, and a surface is created from them. So that on the right is just showing you an example where you've got various objects that are being scanned, and so it's trees in a field, you can tell, and then below that is the same data, but we've removed everything that appears to be canopy. It seems to have done a pretty good job. What you would then do is use an interpolator to figure out what the elevations are where the points from the digital surface model have been removed. And this just gives you a sense. These tend to be iterative approaches, right? So you start with in the upper left with all your data, and you run one of these analyses and get rid of a certain amount of canopy, and then more canopy, and finally you're left with something that looks pretty smooth and appears to be the bare Earth surface. And here's an example of what you're getting when you're done processing your data. These are maximum heights for an area in Isle Royale Island. This is work from Mike Falkowski. And so red areas are higher, blue areas are lower. So maximum height is obviously one thing you can get from these systems. Total canopy cover. So if you know how many points in a particular area hit the ground, then you can use that percentage of all the points that have hit the ground as an estimate of canopy cover. Now, the interesting thing is you can then look at the canopy cover at any level. So this is giving you an estimate of just the understory canopy cover, places where you have, say, shrubs or small trees that are under taller trees. So lots of applications for forest LiDAR, inventory, of course, but there are also sort of more subtle applications. So this here is LiDAR used with a wildlife habitat suitability model. So it's essentially coming up with an index that tells you how suitable a particular area is for a hairy woodpecker. This could be done in the field, but it can also be done with estimates of forest structure variables such as basal area or the density of snags that you can get from LiDAR remote sensing. So you've got actually published habitat suitability models. You plug the LiDAR data in place of field measurements of basal area and snag density, and then you get a map of habitat areas, and you can look at the areas of high habitat availability, and you can prioritize those areas for habitat conservation. Here's a great application. This is work that's done at CSU and was kind of pioneered at CSU. In tropical landscapes in particular, you have archaeological features that you wouldn't notice in the field because it just looks like topographic variability, but you might notice it if you were right on top of it, but it's very hard to see. It's impossible to see from the air, certainly, and very difficult oftentimes to see the whole pattern in the when you're in the field. So, and I threw this in. There are also terrestrial LiDAR sensors, and they, rather than pointing down to get at a canopy, they're pointed sideways so that you're doing the typical LiDAR process, but you're looking sideways. That's the only way I can put it. So there we have a forest example. There's also a lot of archaeological work that's done with these in order to document what areas were like. So review in Lidar, as in so many other things in life, it's all about timing. Lidar sensors measure the distance between the sensor and the target by recording the time it takes for a pulse of emitted light to be reflected off the target and returned to the sensor. Pulses are not instantaneous, but rather they have a duration, or width, and shape that, in the return signal, is convolved with the intercepted surface area of the target. Beam width is critical to many IDAR applications, especially those involving forests or other vegetation with high cover. Most light seen by the sensor will be reflected off the first surface it encounters. Almost all penetration will occur through gaps in between surfaces, i.e. leaves. Lidar return signals summarize the distribution of intercepted surfaces they encounter. They can either be digitized into waveforms or processed into one or more discrete return distances. Laser scanning patterns have to be fully understood to ensure adequate coverage during LiDAR data collection. Many scanning densities and patterns that are just fine for topographic mapping are not appropriate for natural resource applications. And LiDAR is still not a mature, i.e. a standardized technology like photogrammetry. Understanding each individual sensor and the biases associated with its measurements is critically important.